Right. So, in our course selected topics in decision modeling, now we are into our 22nd lecture, that is single variable unconstrained optimization problems. These essentially the nonlinear programming problems we are discussing. So, within that we are now discussing the single variable unconstrained optimization problems. Now, unconstrained optimization problem in the context of nonlinear programming, we might have the objective function is nonlinear and there are no functional constraints. So, that is the essential definition of unconstrained optimization, that there is nonlinear objective function, but there is no functional constraints. So, it could be single variable or it could be multiple variable. So, you can see in the first case we have a case where we have maximize f x equal to 12 x minus 3 x to the power 4 minus 2 x to the power 6. So, we have only one variable. So, since there is only one variable, we call it the single variable problem. On the other hand, the second example, you can see the objective function is x1 square plus x1 into 1 minus x2 plus x2 square minus x2 x3 plus x3 square plus x3. So, you can easily see that there are multiple variables. Now, multiple variables problems are a little more complex than the single variable problems. In this particular lecture, we are mainly discussing the single variable problems only, right. So, in the single variable problems, for a given single variable differentiable function f x, x equal to x star will be an optimal solution if necessary and sufficient conditions are met, right. So, that is what we are discussing here, that is we have, let us say a function maximize z equal to f x, all right. So, what is the necessary condition? Necessary condition will be df dx equal to 0 at x equal to x star, but we cannot call x star as optimal until and unless it also satisfies the sufficient condition, that means the condition of sufficiency, that the second derivative should be negative, right. The second derivative should be negative. So, this is what happens in case of maximization problem. What will be there for the minimization problem? The minimization problem, everything else is similar. The necessary condition is again the first derivative should be 0 at the point of optimality, but additionally there should be the second derivative should be greater than equal to 0. So, second derivative less than equal to 0 for maximization, second derivative greater than equal to 0 for minimization, right. So, this is what we have to do, right, we have to find out. The problem really comes when we might be able to find out the derivative values, but from the derivative values it may not be possible to find the value of the variable, decision variable very easily, because higher order equations are really involved. So, that is where the problem comes. So, simple problems are easy, but difficult problems, let's look at some of these things before we solve this problem. Let us take a very simple problem. Suppose I have only this problem to solve, that is let us say maximize. Supposing I have this problem to solve, that is maximize f x equal to 12 minus 2 x square, right. So, only this problem to solve. Now, we find what is its say 12 x. So, maximize f x equal to 12 x minus 2 x square, only this much, nothing else. So, if I am solving only this much and not the problem that is given here, then if I find the first derivative dfx dx, then we find is equal to 12 minus 4x. So, when I put equal to 0, I can easily find x equal to 3. What is the second derivative? Second derivative d square fx by dx square equal to minus 4. We can see that this is negative. So, since it is negative, so that means the original function is concave, the objective function was concave, and therefore, the x equal to 3 is our optimal solution. All right. So, once again look what we have done. We have a problem, maximize f x equal to 12 x minus 2 x square. We took the first derivative and we got 12 minus 4 x. We put that equal to 0 and we got x star equal to 3. So, when we got x star equal to 3, that is our optimal solution for maximization, because the second derivative is equal to minus 4, which is negative. There is no difficulty here. All right. So, this simple example is very easy, we just solve and there is no confusion whatsoever. But what happens in this problem? Let us see now. See, maximize f x equal to 12 x minus 3 x to the power 4 minus 2 x to the power 6. So, if we take the first derivative, we see the first derivative is 12 minus 36 x cube minus 24 x 5, right. So, we see 12 into so minus 2 x 6, so minus 12 x 5. So, this can be shown as dx equal to the first derivative 12 into 1 minus x cube minus x 5. So, this is very easy to verify that is our first derivative. If we take the second derivative, that will be minus 36 x square minus 60 x to the power 4. All right. Now, second derivative is less than equal to 0. Why? Because put any value of x, so x square will be positive term and x to the power 4 will be also a positive term. So, this is multiplied by a negative number and here also multiplied by a negative number. So, whole total must be negative. So, that means the second derivative is negative. So, it is conclusively seen that the second derivative is negative. So, we have no problem here, the second derivative is negative, but what about the first derivative? We have to put the first derivative equal to 0, that is our necessary condition. So, to satisfy the necessary condition, we should have the first derivative equal to 0. So, if you put that first derivative equal to 0, which essentially means that 1 minus x cube minus x 5 equal to 0. Now, this is not going to be easy to solve this, because you will not be able to factorize it so easily. This particular problem may not be so difficult, because equal to 1 equal to x cube plus x 5. So, you can take x cube common and all those things you can try, but then that is not the usual thing, because you may have different coefficients for another problem. We should really find a method where such problems can be solved all the time, not for a given problem. So, one can see that finding value of x is very difficult here in an analytical manner. So, therefore, there are certain procedure which can be called as one dimensional search procedure. Several methods are there. We discuss one method, that is bisection method. So, how do we find out the solution for such problems in a simple manner by an iterative procedure? So, what we can do, you see, this is how we begin. Supposing x star is optimal solution and we are really solving a maximization problem. For a minimization problem it will be slightly different. For a maximization problem you can see the function is concave. So, if the function is concave, you can see that this is where the is our optimal point. So, this is the optimal point. So, the before the optimal point, so this side is x is less than x star and this side is x is greater than x star, is it not? So, what is your basic concept about, suppose I make a small chart, x less than x star, x equal to x star and x greater than x star. So, these are the three regions, right. Now, what is your comment on the slope? See, this side it is increasing slope. So, can we say that slope is positive? This is the point which is the saddle point in the between point. So, slope is 0 and here it is falling. So, slope is negative. Now, we know that df by dx is nothing but slope, all right. So, same thing is noted here, this, if x is less than equal to x star, then the slope is positive. If x equal to x star, slope is 0. If x greater than x star, slope is less than equal to 0. So, this is very easy to understand, that essentially that is what we have written here, right. So, what we do is, basically suppose we do not know the function, but we take 2 points. Suppose we take one point here and one point here, is all right. And then this where from we get these 2 points? It is not that these 2 points has to be exactly on the both sides, but we should be able to find 2 points which we know very much with certainty, that one is on this side and the other on the other side, that we should know. If we know, then what we do, we take the average, supposing the average is here, right. Now, for that average we find out the slope or the gradient. Then we simply check that is the slope negative or if the slope positive. Supposing we know the slope is negative, so suppose this is our original point A and this is our original point B, then if we see the slope is still positive, then we discard this A and call this as A, is all right. Then again we take the average and supposing we get another point, suppose here, so then that we call B and we discard this original B. So, like this, what has happened, again we take average, and by this bisection method we are essentially nearing the point. When we are coming to very close to this optimal point, we may say that yes, optimal point is reached, right. So, this is how the one dimensional search problem actually shall proceed. So, let us see that how it happens. So, initialization, select epsilon, find an initial x bar and x underline and x bar, and then the trial solution is x underline plus x bar divided by 2. So, this x underline is on one side and x bar is on the other side. So, supposing we have a function, so this is our function, so this is our function, this is supposed to be optimal. So, this is your x bar and the other side is your x underline and x bar. Now, the question is evaluate df dx, that means the gradient at the point. Supposing this is our point. So, this is our x dash. Now, look here, supposing the x dash is on the upward slope. If it is, see, this is the upward slope, that means greater than equal to 0. So, if it is in the upward slope, then this point should really come here, right. So, this point goes here, that means x dash will now become x underline, right. So, if df dx is greater than equal to 0, reset x bar with x dash, which is the trial solution, which is the average solution. So, basically this is how we proceed, and similarly same thing we might do in the next case. Then if the slope is on the other side, then take x bar equal to x dash, right. So, how it is done once again? So, this is our plot, this is our curve. So, this is our, let us say, x underline, and this is another point which is x bar. So, this is our x dash. So, if x dash has come in such a way that slope is actually negative, which is falling under that. So, these x dash now should be taken as our new x bar, right. So, that should be reset. So, that is how you do, and then select a new x dash and again follow, and if the difference between the x bar and x underline, the difference between them, if they are within 2 epsilon, then we should stop. That means x dash is within epsilon, because x dash is in the middle. So, if the gap, this is the gap, this is the gap. So, if the gap x is somewhere in the middle, so if the gap is less than 2 epsilon, we may say that x bar is within epsilon of x. So, we can stop, otherwise continue. So, that is how the method is. So, very simple method. Let us see how it is operated. Let us take the example once again. So, the example was maximize f x equal to 12 x minus 3 x to the power 4 minus 2 x to the power 6. So, we took the two derivative df dx, once again it should be 12 minus 12 x 3 minus 12 x 5. So, 12 common, 1 minus x 3 minus x 5, and the second derivative is minus 36 x square minus 60 x 4, which is less than 0. So, that is the first step. Then after that, this is the plot, 12 minus 3 x to the power 4 minus 2 x to the power 6, that is our objective function, to really show that the objective function is concave. Right. So, this shows the objective function is concave. We have also shown the objective function is concave by taking the second derivative, and we saw that the second derivative is negative. So, since it is a concave objective function, the maximization of the function is possible, right. Maximization of the function is possible, because if we would have had a concave objective function, convex objective function, then there was no global maxima, that was not possible to find. So, that is a very important consideration that has to be seen first, right. Now, what we do, that through inspection it can be seen. So, how we see that inspection? So, you can see that this function is going through certain points, obviously it goes to 0 and this side is another point, let us say 2. So, definitely this has to be between 0 and 2. So, 0 is the, supposing where is the objective function. So, supposing this is our maxima. So, maxima will be somewhere here. Now, it is known that this maxima is definitely from a point 0, this is 0 and somewhere here, that is point 2, right. So, 0 will be one side, 2 on the other side. So, if you carefully see the graph, at least one can work out that there should be 0 or 2, right. So, it should be within 0 and 2. So, these two limits are required. So, we must have those two limits first. So, when we have ascertained that those are our two limits, then from those two limits we can begin. So, that means we can say that first of all certain things we have seen, that f x is concave, f x is negative if x is less than 0 or x is greater than 2, alright. So, therefore, we can make use of one dimensional search procedure that we can make with the following initial values, that is x underline equal to 0 and x bar equal to 2, and let us take epsilon equal to 0.01. So, with those values we begin. So, now we first take x dash equal to the average of the 2. So, 0 plus 2 by 2 equal to 1, right. So, 1 will be our new value. Now, we check what happens at point 1. You recall that was our first derivative, df dx is 12 into 1 minus x cube minus x 5. So, when you put that value 1, we find 12 into 1 minus 1 minus 1 equal to minus 12. So, we get a negative. Since we get a negative, that means which side it will fall? Recall, this is our curve. So, this is negative. So, this point must have fallen this side. So, this side means, so this is 0 side and this side is 2 side, right. So, 0 was x underline, 2 was x bar. That means, this new point should be replaced by x bar. So, new value for x bar should be therefore x dash equal to 1. So, that should be our new x bar, right. So, that is the first iteration. In the first iteration, therefore, we find the new value of x bar. So, once we find the new value of x bar, now what happens? Again we find that what was the value? Please now remember once again, x underline was 0, x bar has become 1, right. So, those are the values. So, using those values, we can now find next trial solution, that is x dash, and then that we find 0 plus 1 by 2 equal to 0.5. So, this is going to be our new trial solution. So, once again derivative 12 into 1 minus x cube minus x to the power 5. So, at x equal to x dash, this value comes out to be 10.125, right. So, what is the 10.125? This is a positive value. So, since it is a positive value, now it will fall on the other side, that is 0 side. So, this value somewhere here, right. So, since it is that side, so now x bar should be reset. So, what should be the new value of x bar? It should be reset to x dash, that is 0.5, right. So, if we continue our iterations, so with that again we can have further iterations, and when do you stop? When we see the difference between the x bar and x underline is within 2 epsilon, right. That means x dash will be within epsilon of x star, that is the optimal, right. So, that is how we continue the process. So, all of these can be shown nicely in the form of a table. So, that table let us look at the table. So, this is how the computation goes on, that at the first iteration between 0 and 2 we find 1. Look how the f x dash is increasing. So, then after that the new value of x dash becomes 0.5, then again at the next 0.5 to 1 it becomes 0.75, then 0.75 to 1 the value, see now slowly the value is increasing, and then between 0.5 to 0.875, then 0.8125, like that it goes, and finally at the 7th iteration we find that these values become 0.828125 and 0.84375, and the gap is within the 2 epsilon, right. So, we have this kind of value, that is 7.8839, right. So, then we stop. So, after 7th iteration we have the gap has fallen within 2 epsilon. So, that is how we can actually continue. So, there is the x bar minus x underline is within 2 epsilon, the gap is less than 0.02, we stop our iteration, and final solution therefore becomes 0.8359375. So, all these two x dash and x underline we take again average, and we get the x dash is 0.833 and the function value becomes 7.8839. So, this is how we can through an iterative procedure obtain the optimal solution, right. So, let us take one more quick example, so that we understand our process very easily. So, maximize f x equal to 8x minus 3x square plus x cube minus 2x to the power 4 minus x to the power 6. So, we take the first derivative, that is 8 minus 6x plus 3x square minus 8x cube minus 6x5, and second derivative minus 6 plus 6x minus 24x square minus 30x4, right. So, those are the first and the second derivative. Now, this is the function you can see it is between 0 and 1.2, they are on the two directions. So, through inspection it can be seen that f x is a concave function, it is a concave function, that is the function nature is like this, and the second derivative is also for certain values we have to see explore it further, and f x is negative if x is between x is less than 0 or x is greater than 1.2. So, that means x underline we can take as 0 and x bar as 1.2, let us take epsilon is 0.01. So, at the first iteration x dash comes to 0.6, and if we evaluate df dx at x dash it comes to 3.2854, that is greater than 0, that means this is an upward slope, that means we reset lower values, the lower value will then become 0.6, right. So, again we take average and we get 0.9, and again if we take the gradient we find this time the gradient is negative, that means it is on the other side, that means reset the x bar now, that is on the upper limit to x dash equal to 0.9, like this we continue. So, here is the computation table, like this we continue, and as we continue we finally after 7th iteration we get reasonably good value. So, we have the x bar minus x underline equal to, we stop and the gap is less than this, and these are our final solution, right. So, this is how we can solve the single variable NLP problems by first derivative and the second derivative, right. So, these are on the easier side. Next class we shall see how multiple variables are to be considered, right. So, thank you very much.